Hi everyone, this is Kiyun from the University of Edinburgh, and thanks for your interest in our work. Today we're going to talk about a novel action recognition problem in relation to ambiguity in labeling videos. Can you annotate an action using only one verb? The person in the video is taking the basket, or you can say they're emptying the basket, removing the water, or pouring the water. We observed that this kind of issue exists throughout the dataset, causing difficulties in both training and testing. Here we have a video instance of peeling a carrot, and it's annotated as cut. We have other similar videos that are annotated as remove and peel. The label remove is used in many different contexts. For example, removing a tray from an oven, which is equivalent to take. Because of such inconsistency, even if the model predicts a reasonable label, it will still be penalized. We approach the problem in single positive multi-label learning settings. The goal is to disambiguate the confusing label space by learning multi-label classification, but given only single positive labels. The most naive baseline of this problem is called assume negative. Assume negative loss basically learns binary cross-entropy multi-label classification, but assuming that all unannotated classes are negatives instead of recognizing the unknown. We proposed a solution to this problem by generating pseudo-labels. For example, we have a video instance of a label called cut. We extract the feature of the instance and find k nearest neighbors in the feature space within the training set. This way, it will find all the visually similar instances in the training set. They may have different labels, although they may contain a very similar action. In this example, the other instances are annotated as peel, remove, and chop. The peel and remove are the majority, so we thresholded, and now we have peel and remove as pseudo-labels. Now that we have the real label cut and pseudo-label peel and remove, we propose two loss functions. The first loss is called mask loss, which is a binary cross-entropy loss with unknown labels. The original label is going to be positive always, and the pseudo-labels are unknown, so it basically means we can't be sure if the pseudo-labels we generated are accurate or not. So we don't want to penalize it by putting negative or positive signal, but we're kind of neutral about it. So we want to mask it out and not passing any learning signal to these classes. Finally, we treat the other classes to be negative. The benefit of this loss is that it will work with reasonably noisy pseudo-labels. However, it may not be the best choice when you have pretty accurate pseudo-labels. That's why we propose another loss called pseudo plus single label binary cross-entropy. In this loss, we assume the pseudo-labels are accurate, and we're confident that pseudo-labels are well representing the action of the instance. The original label is going to be treated as positive always, and the pseudo-labels are also going to be positive. They're treated equally as the original label. Finally, the others are going to be negative. This way, it will intuitively work really well when the pseudo-labels are more accurate, but it will deter the performance when you have bad pseudo-labels. The single positive multi-label learning problem requires single label for training and validation, but it does require multi-label for testing. That's why we annotated 40% of the official Epic Kitchen 100's validation set in multi-label fashion. That's around 3,500 videos, and we hired 3 annotators for each video to reduce the annotation noise by looking at the annotator's agreement. As you can see, most of the samples have multiple labels. On average, we have 2.4 labels per video. This is the distribution of our annotation in orange compared to the original Epic Kitchen's annotation in blue. It shows that we cover almost the entire distribution of the original annotation. We also summarize the co-occurring classes from the annotation. In this matrix, we see that this point has a high value, and it means when you have a verb put, the verb insert occur together oftentimes. We ran experiments with 6 SPML baselines, and this is the performance you get in F1 measure. This is trained on the original Epic Kitchen 100's training set with single labels. We validated using the 60% of the official validation set with single labels using accuracy metric. excluding the 40% of the samples that we annotated. We test using our annotations with the multiple labels. Our methods outperformed all of the baselines by a significant margin. The reason is that unlike other baselines that only rely on model predictions, we take pseudo-labels from the real annotations from other videos. This way, we can correctly model the confusing label distributions where annotators interchange multiple labels. We also introduced a new dataset called Confusing HMDB 102, which is the same video data as HMDB 51, but we increased the number of classes from 51 to 102. For each class C, we split it into two classes. We choose one random label out of the two for the training videos. Both of the labels are included in the test set. You can think of this as a simulation of having two similar labels for the two ambiguous visual actions. We saw significant improvement in performance with our method in this dataset as well. Again, we are taking pseudo-labels from the real annotations, which model the confusing label space very well. This is different from other baselines using model predictions to mitigate label noise. We also observed that class-level pseudo-labeling fails and we need instance-level pseudo-labeling as we proposed. The one with the dagger sign are the performance with the class-level pseudo-labeling, and as you see, they perform dramatically worse than what we proposed. We obtained the class-level pseudo-labels by looking at the test set annotations co-occurrence distribution, just like you saw earlier. For example, in this matrix we see that put and insert co-occur together oftentimes, and so as take and remove. Whenever we see a label put, we by default add insert as a pseudo-label. However, this assumption is wrong because even though they occur together oftentimes, it doesn't mean that put and insert are the synonym all the time. We need more context from the video to assign the labels, and that's why the class-level pseudo-labeling fails. This also shows that the mask loss is safer to use with noisy pseudo-labels. The next ablation experiment shows that our method of generating pseudo-labels is good enough, and we don't need perfect pseudo-labels for the task. The method with the star sign are the ones with the perfect pseudo-labels, and the other ones are our method, and you see that it doesn't necessarily perform better than our methods. We show this by running this experiment on the confusing HMDB 102 dataset, because we can easily generate perfect pseudo-labels in the training set and bypass our pseudo-label searching pipeline. The mask loss with perfect pseudo-labels is actually worse than the mask loss with neighbor searching. This is because by having the perfect pseudo-labels, it will always mask out the valid labels, which is not necessarily better. In summary, we show that the ambiguity in current action recognition labeling leads to issues in training and testing models. We show failure cases on challenging dataset where the model predicts reasonable labels, but the accuracy is penalized because of label ambiguity. To mitigate the issue, we introduced two novel approaches for training multi-label action recognition models when only single positive labels are available. Our approaches attempt to disambiguate the label space by generating pseudo-labels from similar instances that are labeled differently. Lastly, we introduced a multi-label subset of the Epic Kitchens 100 validation set for the purpose of multi-label evaluation. On this dataset and another with synthetically generated label ambiguity, we report results that outperform existing methods. Thanks for watching the video, and please check out the paper for more experiment results and the details of the datasets. The GitHub link is down below, and in the GitHub page you can also find the link to the paper. Thank you.